Hello, in this video we study transition matrices and similarity. In my opinion, similarity is one of the most important properties in mathematics. Okay, so look at this picture. You have some vector space V, okay, and then you consider some map linear transformation, which is corresponding to matrix A. So you go from V to TV right here, and suppose that in vector space V you consider some basics B. You have coordinate of V in the basics B. So since T is linear combination, we know how to find coordinate of TV, right, in that basics. Now you have another basics B prime, okay, and you want to find coordinate of V in B prime. We learned that topic, how to change basics using transition matrices, right? So let me remind you a little bit about that, and then we move to linear transformation, right? Let's talk about these two. Let's talk about these only two objects, B prime and B. So if you have B, right, you want to go to B prime, you need to find transition matrix. Transition matrix, let's say A, let's say P, from B to P prime, right? How to do that? You just write B prime in here and B, right? You solve this system of linear equations. Actually, you have many systems in this situation. You use row elementary operation to get the identity matrix in here, and here is your P, the transition matrix. But this is from B to B prime. Makes sense? And if you want to go from B prime to B, you just apply the inverse matrix of this guy. Agree? So once you have the transition matrix from B to B prime, you apply this to vector V in B, so you get V in B prime. That's what we learn about, how to go from one basics to another. Makes sense? All right, so in this picture, they write P right here, right? But this is fine, this is how we go from B prime to B. So basically, if we go from B prime to B, so, this matrix should be the inverse of the one when we go from B to B prime. Makes sense? So we know that if we have a linear transformation, we have some matrix representation of that transformation, and that presentation is not unique. It depends on the basics, right? So when you change the basics, you would have another representation of the same linear transformation. Makes sense? In this picture, you see some diagram, right? Diagram right here. You see some diagram right here. So if you go from with the basics B, you go from V to TV, and with the basics B prime, you go from V B prime to TV prime. And this diagram is commutative. The commutative means the diagram is closed, right? So using this diagram, we may find representation of a linear transformation in a new basics, and you also can find coordinate of image of some vectors in the new basics. That is the main topic today, and at the end we will talk about similarity. Okay, let's consider the following example. So you have linear transformation from R2 to R2, and in the standard basics, this linear transformation looks like this. Of course, we know how to find the representation in the standard basics, right? But now they ask us to find the matrix A prime of T in the basics B prime is 1, 0 and 1, 1. So now they consider another basics and they ask us to find that matrix. Okay, so first we write the matrix of T in the standard basics. From here we can get actually AT is equal to 2, -2, and -1 and 3, right? We just pick entries in here and then pick all coefficients of them and write in the row form. All right, now we want to find the representation of this in the new basics. So that means, look at this diagram. We want to find A prime right here. Makes sense? So you have to go from the standard to the new one. That means you have to apply the inverse of this matrix. Makes sense? So basically, I need to find the transition matrix. Transition matrix from the standard basics to B prime. You need to write in the following form. You need to write B prime in here, and then here is the identity, because that is standard matrix. So basically you need to find the inverse of B prime, right? Where we say B prime is what? Is the 1 0 and 1 1. So I write vectors in B prime in the column form. I need to find the inverse of this matrix. Make sense? All right, so we know the formula of the inverse of this guy is 1 over determinant. Determinant is in this case just 1, right? In here I have 1 1 and I take -1 and 0 right here. So that is 1 -1 0 and 1. All right, so I have the transition matrix from the standard to B prime. Okay, and now I will find A prime. How to find A prime in this case? Look at this picture. How to find A prime in this case? So if this diagram is commutative, you will think A prime is equal to B to -1, A, and P. Why? You look at this diagram. So you may think, yes, you are, for example, you are right here, right? You are right here. You want to find A prime. So this is the first vertex of you. Okay. This is the fourth one. Okay. This is the second. And this is the third. Imagine you have this 1, 2, 3, 4. And you want to go from 1 to 4. Makes sense? That is the map. So this vector is equal to sum, right, of this guy, and then the second guy right here, and then the third guy right here. Makes sense? So that is nothing but the composition of 3 linear transformations. Right? So if this is A prime, this is A, this is the P, that is the P inverse. So A prime is the composition, right, of P, A, and P to -1. Makes sense? So we already learned about that. If you have composition, you may define the matrix of compositions, right? So the matrix of composition A prime would be equal to, you take the matrix product, right? But in the reverse order. So that is P prime, P to -1, A times P. That's why you have A prime equal to P to -1 AP. And now you already have P. I would say, yes, this is your P. Okay, so this is your P to -1. So from here you have A prime equal to 1 to -1, 0, and 1. A is 2, negative 1, and 3. That is the matrix in the standard basics. And P is 1, 1, and 0, 1 in here. And you multiply them together, you get the answer 3, negative 2, negative 1, and 2. That's how we can solve such a problem. So the most important in this problem is to understand this identity. Right? So we say that the diagram is commutative. And in that case, A prime is composition of P, A, and P to negative 1. So the matrix of that linear transformation of that composition is just matrix product of P to negative 1, A, and P. Alright, in this example, we consider two basics, B and B prime, as in your screen. And they give us A, just the matrix of some linear transformation in R2, and they ask us to find the matrix A prime for this linear transformation, but with respect to the new basics B prime. Okay, so we do almost the same. Here you have 1 point, so I just want to make a diagram. That is A, that is A prime, so this is B, that is B prime. You go from here to here, from B prime to B, so you get matrix P, and then you go here, you get matrix P to negative 1. So the A prime is equal to P to negative 1, A, and P, where we need to find P and P prime, right? So in order to do that, you need to find transition matrix from P prime to B. Makes sense? So this is, if you want to go from B prime to B, you need to write B and P prime. Okay, so and then you make some identity right here, and then you have the P. In this case, that is transition matrix from B prime to B, and then you apply the inverse, right? You take the inverse of this matrix P, you get P to negative 1, right? And then you just apply this identity. Okay, let's do that together. So we have B is negative 3, 2, 4, negative 2. Don't forget that we need to write, in the column form. Okay, and then here is negative 1, 2, and then 2, negative 2. So you need to use row elementary operations. I want to make 1 on the first row. I want to make this guy become 1, so I multiply the second row by 2, add to the first. I have 1 in here, I get 0 in here, I get 3 in here, and I get negative 2, right? 2, so I have 2, negative 2, 2, and negative 2. So I think I can simplify by 2, I guess. I just write 1. I just write 1 in here, negative 1, and 1, and negative 1. Okay, and then I multiply the first row by negative 1, add to the second, I get 1, 0, 0, negative 1 in here, negative 3, negative 2, negative 1, I have negative 2, negative 1, I have 1 in here, and then I make the identity matrix right here by multiplying the second row by negative 1, I get 3, negative 2, 2, and negative 1. So that is my transition matrix from B prime to P to B. And then you take the inverse of this guy, right? The inverse of this is, let's say, P to negative 1, to negative 1, inverse. We apply the formula, that is 1 over negative 3 plus 4. And here I have negative 1, 3, 2, and negative 2, right? Basically, that is negative 1, 2, negative 2, and 3. And then you can find the matrix A prime equal to P to negative 1, A, P. So you just multiply them together. Negative 1, 2, negative 2, 3. What is A? A is given right here is negative 2, 7, negative 3, 7. Negative 2, 7, negative 3, 7. And another one is 3, negative 2, 2, and negative 1. At the end, you would get 2, 1 and negative 1, 3. That's it. Now let's talk about similar matrices. In the previous example, we already see the following formula. A prime equal to p to negative 1 AP, right? Where A and A prime are matrices of the same linear transformations in different bases. So, such matrices A and A prime are said to be similar. Okay, similar. So basically, what's that? Similar matrices are matrices of the same linear transformations in different bases. That's it. But if you look at this from the point of view of algebra, yeah, that is the only, property. That is the only identity says, yeah, these two matrices are similar. That means you can go from one matrix to another using some invertible matrix P, right? So, you can find some invertible matrix P. Well, from here, you would think, yeah, actually A in this case is equal to P, A prime and P to negative 1, right? So that is nothing but P to negative 1 to negative 1, A prime, P to negative 1. Makes sense? This is also of this form. Agree? All right, let's consider the following example. Like A equal to 2, negative 2, negative 1, and 3. And A prime is equal to 3, negative 2, negative 1, and 2. They are similar. Why? A and A prime are similar because there exists a matrix P such that 1, 0, 1, and 1, right? Because for this P, you have A prime equal to P to negative 1, A and P. That's what we saw in the previous example. Okay, and in the second example, we also saw that actually this matrix and the matrix A are similar. This is really important. Important in the sense that if you want to apply A prime square, right? You would think, yeah, that is P to negative 1 AP times P to negative 1 A and P in here. And actually you have P to negative 1 A. P with P prime gives you identity, right? So we don't write it, we have A squared P in here. So basically, if you have two similar matrices, you can apply functional calculus for those matrices at the same time. Make sense? Like this and this. That is, that is really important in matrix computation. Look at this. Here's a good example, right? Suppose you have some diagonal matrix A. A is diagonal matrix. I write in this form, just lambda 1, lambda 2, and lambda n, right? All the entries are zeros. Make sense? And you have some matrix A prime, which is similar to A. So that means A prime is equal to P to negative 1, A, and P. Make sense? And you say you want to find, A prime to the n. Of course, this is too complicated, right? If you have 1, 2, 3, 4, right? Just 2 by 2 matrix, and you want to find A to the n. That means you multiply A and A n times, right? It's too much. If M is big number, so the complexity is too high, right? So I want to do in a faster way. I say I need to find some diagonal matrix which is similar to A prime, if that matrix exists. And suppose that in some basics, our linear transformation has diagonal form. Makes sense? Has diagonal form. So you can find A prime in that basics, right? in that specific basics. Okay, so now you can multiply a prime to the n. As we have seen right here, you just need to apply p to negative 1, a to the n p, right? But what is a to the n for diagonal matrix? For this diagonal matrix, a to the n is nothing but diagonal. Lambda 1 to the n, lambda 2 to the n, and so on, lambda n to the n. Otherwise, all the entries are 0. Make sense? So it's very easy to do with diagonal matrix. That is one application of similarity of matrices. Make sense? So from this observation, it arises a question: how to find basics in which the matrix of our transformation is diagonal. And that is the question of the next chapter. Okay? Before we finish this section, I would like to consider one example with 3 by 3. And then, we finish this section and the chapter. Let's consider A equal to 1, 3, 0, 3, 1, 0, 0, 0, negative 2. This is the matrix of some linear transformation from R3 to R3. This is obvious because the matrix is 3 by 3. Okay, and this is the matrix in the standard basics. They ask us to find the matrix A prime in the basics P prime 1, 1, 0, 1, negative 1, 0, and 0, 0, 1. Okay, so again we need the diagram. This is A prime, this is A, this is standard, which is B. Here is B prime, here is TB, TV in B. Okay, here is TV, but in P prime. Here is matrix P, here is the matrix P to negative 1. So you need to find the matrix P from P prime to P, right? If you go from P prime to P, that means from P prime to the standard. So you already have the matrix P right here, because that is 1, 0, 0, 0, 1, 0, and 0, 0, 1. Here you have 1, 1, 0, 1, negative 1, 0, and 0, 0, 1. Right? So this is your matrix P. From here you can find the P to negative 1. You can do that yourself, but the answer is 1 over 2, 1 over 2, 0, 1 over 2, negative 1 over 2, 0, 0, 0, 1. Once you have P and P to negative 1, you can find A prime equal to P to negative 1, A times P. That's it. Okay? So I hope that, all examples in here are clear, and I mention again why similarity is one of the most important properties of mathematics. And as we have seen that, two similar matrices are just representations of the same linear transformation in different basics. So changing basics is very important, and to find a basics with respect to which the representation is diagonal is also a very important question, right? Thank you, and see you in the next video.